Welcome to session 2, Innovation on Marine Renewable Energies. Innovation needs to happen every day in this sector, within the small companies and throughout the value chain. In order for this to happen, we need mechanisms and projects that support openness. If the challenges are to be met with knowledge, experience, and human ingenuity to solve things, the information needs to be shared. It needs to be tackled in many ways and together. Many thanks to WavEC at this occasion that brings us together today to foster innovation through exchange of ideas and thoughts. I would like to introduce Emiliano Pinori as the first speaker from Research Institutes of Sweden, and he will talk about and give an overview of the Oceanic project.
Yes, thank you everybody to be here. Thank you the organizer for inviting me. As Pierre said, I will introduce you this Oceanic project that is a co-founded project from the Ocean Aeronet. This is a brief presentation, so I will say it already now. We will not have, again, the project will start in December, will stop in December, and I will see some preliminary results. We are still working on that because of the weather, because working on offshore, you know that it's not easy all the time. So the idea of this project was to try to innovate in something that is quite old and is used for many years ago. This is from actually a previous project from others, from Spain. And so the work company tried to protect metallic part in the environment by using thermal spray aluminum. I don't know if so as you can see here, when you immerse thermal spray aluminum or metal, so there is something called biofouling in the ocean. Especially the problem here is the barnacles. So when the barnacles attack the aluminum foam of the thermal spray aluminum, that is a protection against corrosion, this aluminum will corrode very fast, so you will lose your 20 years of protection. That is what you're aiming for. So we thought there was maybe a possibility to mix together, anti-fouling properties inside this thermal spray aluminum. So that's what Oceanic is about. It's not an anti-fouling solution for boats or stuff like that. It's more to regain the lifetime of the thermal spray aluminum layer by adding a protection against especially barnacles. The project is have a partner from Portugal, WavEC, and then we have people from Spain and Basque Country also, and then 3 partners from Sweden. We have been testing in Portugal, in BMAP, that is in Basque Country, and also together with WavEC, we have been testing also in EMEC. Now I will have a 3 minutes video, just it was like for 1 year ago, just to give you a brief introduction what is Oceanic, and then I will go with the final results. I don't know if there is the audio or no.
Ocean energy devices and components are subject to one of the most aggressive environments. Corrosion, mechanical stress, but also biofouling and biocorrosion challenge the reliability of materials used. The ocean energy sector needs a service protection system dealing with a very hard challenge. A novel technique has been demonstrated in the EU project LEAF. The new approach in anti-fouling has shown efficiency and have the potential to last for more than 25 years against barnacles with trace emissions of organic biocide. More important, this approach is contact active and thus open for novel applications, even not paint-based. The Oceanic project will embed this new anti-fouling technology into a polymer carrier, and then mixing it with the well-established thermal spray aluminum technology will create a sprayed composite coating, achieving long-lasting protection against corrosion and biofouling in the marine environment. The modification on the TSA gun with the addition of a feed system to add air-suspended polymer powder at a certain distance and angle with respect to the arc plasma nozzle has been prepared. Different setup has been used and 4 different panels have been sprayed. The samples have been prepared to be analyzed in cross-cut by scanning electron microscope SAM and by energy dispersive X-ray analysis EDX. The results of the SAM are shown in the black and white picture. You can see here the porosity coming from the polymer powder in the darker layer in the middle of the sample. In the EDX picture, the different materials are represented with different colors. Green is aluminium, blue is the polymer, as can be seen also present inside the aluminium layer. Red is the super duplex steel substrate that is used. The polymer used here is not yet the one doped with the biocide. This is under preparation and several panels will be deployed at our 2 test bed sites in Pinori, Portugal and BIMEP in Spain to check efficiency against corrosion and fouling during summer 2017. Oceanic gathers 8 partners from 3 different countries, Sweden, Spain and Portugal.
So as you see, this video was 1 year ago. Now we have put the anti-fouling or anti-barnacle molecule inside the polymer and we have sprayed these panels. And as I said, beside Portugal and Spain, now we have been testing also in Scotland, in Orkney. So just to remind you, you've seen the video, but the arc technique is, the arc spray is that you have, in this case, wire feed is aluminum or other alloy, and you, with compressed air. So the temperature is quite high there, but we have analyzed that the polymer and the substance is still alive once embedded in the aluminum foil. At the beginning, we did it in a very easy way. As everyone knows, when you have the TSA layer, usually you put a sealant, is a silicone base, and we put the abamectin there. This was the first generation. So we had very good results, but of course, this means that when your layer is finished, is deployed, then you will never have this 20 years of protection against the barnacle. So you maybe just postpone it with 1 year or 2. So we went for the, as said, for this modification of the gun and tested and analyzed of the results. So this is our, what we call second generation. And as you've seen in the video, this picture. So we could see that actually the polymer with this molecule is called abamectin is inside there. And we tested here in Portugal. Then we moved from offshore to near shore. In BIMEP and here in EMEC together with Corpower. So here you can see some results finally. These results arrived from just 1 month ago, and we still are analyzing the results from Portugal and from Spain, and some of the panels are still underwater. But as you can see here, the left side, you have the panel with the powder, with the polymer carrier with the abamectin. And in the right side, you have it the same setup, but inside the power, we don't have any abamectin. So it's the same material, the same structure, just abamectin or just this anti-barnacle molecule that is missing in the right side. So you can see that this is from EMEC, and you can see that there is a difference in how much the barnacle can grow on that. There are several replicates because now I'm not going in detail, but we have different alloy and different kind of polymer. But it seems that all of them are giving significant results, at least preliminary. As I said, we will come out with final results at the end of the year. Then what we needed was to try to improve this because, okay, it's better than the control, but it's still growing some barnacle. So what we did was to move from the generation 2 that has approximately 25% of polymer when you spray it, and we modify it again, and we enhanced the amount of polymer from 25 to 35, 34. And this is the analysis of this third generation of the polymer. You can see there is a little bit more of porosity, a little bit more of polymer. And we applied this, not this time on panels, but on what we call devices. Okay, it's shackled and high bolt. And this was put inside the harbor in, I think it was in Deba. So it's in Basque Country. And this is not 1 year, but still, usually here it grows a lot, even from September. So there are a lot of barnacle everywhere in this period. And you can see that here, at least as much we can see, there are no barnacle. There are some slime, other stuff, but we are most interested in barnacle because of their influence on the aluminum layer. So we can see that we have tested and produced different alloy. We have tested them and worked on different polymers. So now we know a little bit more which polymer are working, which alloy are working best. We have managed to do this all-in-one anti-corrosion, anti-barnacle. We will also have, Pedro will present another part of the project was to produce a database, not based only on our results, but on all the results, even for 30, 35. Pedro will tell you more, but it's a database that will be open to everyone to consult what's growing where. Yeah, and then, as I said, final report will be on our website, so I hope that we will be able to put that in somewhere in December, before Christmas, if the weather and the waves will permit us to do that. So thank you very much. If you have any question.
I welcome Pedro Vinagre, Senior Researcher and Project Manager at WavEC, to explain the Oceanic project and the biofouling database.
Okay, thank you, Pierre. First of all, I would like to apologize. Today I'm a bit under the weather, so I may not feel as clear as possible. I would like to thank the presence of the audience and all the speakers. Like my colleague Emiliano said, we did several trials in different countries. But besides evaluating the efficiency of these coatings, one of the outputs was to, I don't know why this is going forward. One of the outputs was to develop a biofouling database for the ocean energy sector. So, firstly, what is biofouling? Biofouling is any kind of marine growth adhered and settled in artificial man-made structures, such as pontoons, buoys, and any kind of equipment set deployed at sea. There are, to be referred, over than 4,000 organisms responsible for biofouling, and it is divided into microfouling, including microorganisms, such as bacteria, fungi, and microalgae, and also the macrofouling, which itself divides into soft fouling, namely soft organisms, and hard fouling, which are the hard-shelled organisms. Some examples of biofouling: you have different kinds of crustaceans, annelids, gastropods, and bivalves. So in this database, we focus on 5 main biofouling groups because these are the groups that are the most problematic within the ocean energy sector. Namely, the macroalgae, the kelps from order Laminariales. They cause great abrasion and alteration of hydrodynamic properties of devices. But since they are mostly they are neutrally buoyant, and they only mainly impact moving devices. Following the bryozoans, which also cause abrasion and accelerate the corrosion of materials. And some hard-shelled organisms such as the mussels, barnacles, and calcareous tubeworms, which mainly exert substantial weight and increases the diameter of equipment and the roughness of that equipment. The problematics of biofouling are that offshore structures at sea, they mimic artificial reefs. This has positive aspects, meaning that they will attract marine organisms and eventually promote ecosystems diversity and function, and may even be used as a sanctuary for endangered or commercial species. However, because of this, they also contribute to the propagation of non-native species, and this will eventually also impact biodiversity and may also pose economic threats, for example, in aquaculture. So there are no requirements per se directly related with biofouling. However, they are regarded in several pieces of legislation as a vector of non-native species propagation. And the aim of these legislations are to prevent the introduction and spread of non-native species. There are also some engineering and environmental standards related to biofouling. However, they are many times applicable at local level and not adaptable to other regions. So why to develop such a database? We found that the knowledge on biofouling is not being well or properly transferred across sectors, across maritime sectors. And this many times leads to improper design of devices, of operation and maintenance methodologies, and of course this all means increased costs. So our database aimed to allow the ocean energy sector and others for a more informed and quick decision. For example, when selecting a site and the frequency and type of maintenance. How did we do it? We selected a few sections, namely we divided, this was developed for Europe at the moment. We divided, we searched for literature within biogeographic regions. So we have an overview of countries encompassed in the mapping. At present, we included 9 countries, 9 ecoregions, sorry. Then within ecoregion, we selected the countries. We have up to now 24 countries. Following the distance to shore, this is the distance in kilometers between the sampled site and the closest continental land, which range from 0.1 to 195 kilometers. The type of equipment, firstly we focused on ocean energy equipment, but due to the scarcity of data, we also search for literature on oil and gas sector, aquaculture, another artificial reefs, and also in test panels. We also included the period of immersion, which was the time in months or years during which the biofouling could grow. This, we found data from 1 month to 39 years. The depth at which data was retrieved, from, in this case from surface down to 90 meters depth. Then we added the species qualitative and quantitative information, mainly the biofouling thickness and weight of samples, and the size or length and weight of the organisms, the hard-fouling organisms. And finally, of course, we reference the authors that reported that data. The main findings were that number of species would increase up to down to 90 meters depth and decrease largely to the bottom. And depending on cold versus temperate, warmer waters, you would have a first band of green filamentous algae, followed by kelps and accompanied by barnacles and mussels up to the 30 meters, and then very different kinds of mobile organisms down to the bottom. Interestingly was that we found in this data 17 marine non-native species already, all reported within the North Sea. And they were finally mainly found at intertidal, and mainly they were barnacles. So this is the aspect of, you have this pamphlet in your bags. This is the aspect of the database at the moment, where you have all the sections I mentioned. You have the website where you can download the database, and it's online since mid-November, and we already had a few downloads around the world. This is a form that we ask for you to fill with your name, your city, your company name, the sector you are working on, and if you're using this database for a commercial or investigation use. This is only for statistical purposes. Thank you very much.
Invite Patrik Möller to the scene, to the stage. CEO for Corpower, been in the ocean, testing at EMEC, and we look forward to hear about your step changes to accelerate the learning curves.
Thank you, Pierre. Very excited to be here. Thanks for inviting us. Since the last seminar that we spoke on as well, we have had some major developments in Corpower. We've gone through a phase of dry and ocean testing, and today we'll give you an update to that with some very, very encouraging results, we believe, for the wave energy sector. First, what are we up against? Well, we heard before the question, why has wave energy not succeeded till to date? We believe it's very clear that wave energy devices until today have either been breaking in storms, or they've basically been too large, too costly compared to the energy they've been able to produce. And if you look at the technical challenge behind that, the challenging part is that you often have very high peak loads, which drives the sizing, the dimensioning, and thereby the cost of the devices, whereas the average loading is on a lower level. And if you have too large differences between peak loading and average loading, it's hard to make a business case. And that key challenge is what we are addressing and changing with the technology we're introducing by Corpower. To do that, we're introducing a few innovations to wave energy. Our buoy is a point absorber. It's a pre-tension composite buoy moored to the seabed. You see the cable coming out at the bottom. If we look inside the composite buoy, we have a few innovations that make wave energy more effective. The first one, it's a pre-tensioning technology. Instead of loading the buoy with a lot of mass, we pull it down to the midpoint by an air pre-tensioning system. The effect of that is that the natural frequency of the device that it wants to oscillate with in its natural state is much faster than any incoming wave of an ocean spectrum. This means that it's a very poor absorber of energy. It doesn't respond to the ocean waves. And this is the detuned protection state that we use in our device in storms. When we put it back into the natural state, it's very transparent to incoming wave. What we then add on is a new invention called the wave spring, which is a negative spring that changes the stiffness of the system. Doing that makes us resonant in all incoming waves of a typical spectrum. So it's an on and off control. On the buoy here moving in the tank, you see how the buoy actually makes a motion which is 2 to 3 times higher than the incoming wave itself. This is due to phase control, and the resonance effect amplifies the motion 2 to 3 times and 5 to 10 times higher velocity. After this, we add a new solution that we call a cascade gearbox that we use to translate this amplified linear motion into rotation with a very robust and high efficiency type of gearbox that has a high degree of damping. So these three innovations together bring new solutions to wave energy that makes it possible to become much more competitive compared to the past. If we look at this is the PTO, what it looked like in our stage 3 equipment. And if you look at some of the metrics that we've been able to show so far, if you look at energy per force or energy per volume, basically how much you can extract from a given buoy volume, we've been able to show 3 times as much energy compared to the prior state of the art. And if you look at energy per ton in structural efficiency, which was mentioned in previous talks today as well, we've been able to increase it 5 times compared to the previous state of the art. And with these solutions, we bring wave energy to a similar structural efficiency as the most competitive offshore wind turbines of today. So it's a major jump for the sector. And to prove this, we've been going stepwise. We followed a structured verification approach where we started small-scale tank testing, actually here in Portugal, in 2012 and 2013. We got very good results, and that could motivate investment into a next stage of testing that we did in France in 1 to 16, and we built our first PTO test rig, which we have here, that we were running in Sweden between 14 and 16. And now recently we've just completed our stage 3 demonstration that we've been running in Orkney. And it's been a 3-year project overall for the design, fabrication, and dry and ocean testing. And I wanted to give you an update on the results we have now shown there. We can say that the first phase of the project, we've been going through an extensive dry testing phase. This part was funded by Wave Energy Scotland and the program David mentioned before, together with the Swedish Energy Agency and InnoEnergy. And we've been starting to put the devices together, and being able to have a simulated wave environment in a hardware-in-the-loop test rig, we could start with low energy waves, low motion, and start debugging and stabilizing the equipment. I think we've corrected somewhere around 100 different small issues with the equipment until we could have it fully stabilized and achieve the uptime, the availability, and by the end of the dry testing period, we took it through full range storm loading that we could simulate here in the dry test rig. After that, by September of last year, we shipped the equipment to Orkney. This is what our half-scale device looks like when it arrived in Orkney. It's a 4.2 meter buoy, 15 tons. And we then installed it here at the SCAPA flow test site, which is a nursery site of EMEC. And we had the opportunity in the ocean test program to go through 3 rounds of installation and retrieval when we were optimizing all the auxiliary components around it. So today we have been down to around 1 hour cycle time for either connecting the device after having positioned the vessel and arriving at site. So we've been developing very effective and low-cost operations and maintenance methods here using multicast with day rates in the few thousands of pounds per day. And with this, with the installation in Orkney, we have been connected to a microgrid, to a floating microgrid located on this test and support buoy. And we've had a data transfer and the communication through radio link to shore. When we did the testing in the dry rig in Sweden, we were grid connected. So in that sense, we've proven the grid quality when we were dry testing it. And here we've proven the market application for off-grid, more islands and other offshore installations in the installation in Orkney. And since the installation, we've been going through a range of fairly large storms. We have seen winds up to 50 knots, and we have had here waves up to 4 meters, individual waves with a half-scale device that is equivalent to 8-meter waves in the full-scale equipment. Here you can see the device operating in this detuned storm protection mode. And you see how the device is essentially standing still where large waves just pass by it. The device becomes transparent to incoming wave energy, and you can compare this function to a wind turbine, which is pitching down the blades in high storms. Essentially, every commercial wind turbine on the market has that capability today of pitching down the blades to avoid overrunning in storms. And we're adding that same functionality to wave energy with our technology. So that has been proven to work extremely well, and the loads we've measured in storms are actually not higher than the loads we're measuring in the moorings in regular operational sea states. If we look inside the device, when we ran it tuned, you see a large motion, and we've been able to verify the energy production in all the relevant sea states that you could experience in SCAPA flow test site. And very encouraging, we've actually proven that this transparent protection mode has worked really well. We've shown survivability throughout all the weathers experienced. And the power production in all sea states measured has been slightly higher than predicted by the simulation models. So that has been one of the most encouraging outcomes of the testing. Combination of survivability and effective power production. And this new wave spring technology has been proven to have a very high efficiency. So if we're summarizing that, we can now confidently say that resonant wave energy is a reality. And the transparent protection mode is probably the most important feature that we bring to make wave energy reliable. We've proven an annual production which is increased by 300% for the same size of buoy when you use the wave spring control technology. Looking at the structural efficiency, how much energy we get per ton, we are above 10 megawatt hours per ton on the very first full-scale prototypes. If we compare that to some of the wind float numbers mentioned before, around 300 tons per kilowatt, this corresponds to about 200 tons per kilowatt in our very first generation full-scale equipments. So we think we're taking wave energy to a major step forward in this. And getting a lot of energy from a fairly low-cost small device gives a low capex per megawatt. And then small lightweight equipments are also cheaper, easier to handle with low-cost vessels, which drives down the operations and maintenance cost. And altogether that contributes to a clear path to 100 and to 50 euros per megawatt hour when the volumes increase. And in stage 3, we've been going through a certification program together with DNVGL, where we have achieved a statement of feasibility. And in the next phase, we're now looking to have a full prototype certification on the equipment. We've also done a lot of learning by the testing we've been doing over the last 18 months. And for us, one of the big conclusions is that dry testing is essential. There are so many small things that you could and should find on control environments on land before you put anything in the ocean. So in full scale, we will continue to invest in dry test equipment that can provide equipment with full range loading up to storms. And we've also concluded that all the wet systems around it, most of the downtime we had in Orkney was actually due to the auxiliary systems such as the anchors, the tidal regulation, the microgrid. It's as important to pre-qualify those auxiliary systems, of course. Having done the dry testing, we achieved a very good availability of the wave energy converter itself. And in our next programs, we will have a larger program pre-qualifying the wet kit, if you say. And C3 was our first equipment that we put in the ocean. It was a research machine to prove the performance and the survivability in the storm protection mode. Next time, we're now aiming for a significant reduction in complexity, doing the same functions with less parts and driving down the cost with that. And our vision now for 2023 is to have a fully bankable product proven through ocean testing with at least 3 devices operating in an array. And we are going to clock at least 8,000 hours of operational data on these so that we can get it certified for availability and the yield. And we plan to do this in 2 more stages, what we call stage 4, which is a single device full scale, which we are currently in the design phase of. Construction is scheduled to start after next summer. And then another array phase of adding 3 more devices to this installation. And we are having a big part of the program already funded. We're still in discussions with multiple places for where to go. Portugal is one option where we might end up with this demonstration. And if we end up here in Portugal, we intend to build out a significant supply chain, essentially everything around the system from the composite buoy, the foundations, the moorings, the electrical infrastructure, and of course the operations and maintenance installation work will be developed here in Portugal. And in Sweden, we will do the drivetrain, the PTO itself, which is sitting on the inside of the equipment. So we're looking at setting up a operations and maintenance base in the north of Portugal. If we go here, we will be using the Agusadora test site together with EDP. And we found very attractive facilities where we could build out both for having the final assembly between the composite buoys and the drivetrains itself, and how to do the operations and maintenance. So we're very excited about the opportunities of taking wave energy to a fully proven commercial solution here. Thanks.
Many thanks, Patrik. We move on in the schedule. And I welcome Eduardo Gorbeña, research at Marine Offshore Renewable Energy team, and we'll talk about marine offshore renewable energy synergies with UK institutions. Welcome.
Okay. Thank you, everybody. I would like to thank WavEC for the presentation. So the objective of this presentation is to give an overview of the projects that the Marine Offshore Renewable Energy team from the University of Algarve is involved, and what is our relationship with UK institutions. I will start this presentation giving a brief introduction of the Center of Marine and Environmental Research from the University of Algarve, where the MORE team is inserted. Then I will present the projects that we are involved, and finally I will end with what we can offer. Okay, so the Center of Marine and Environmental Research from the University of Algarve is a multidisciplinary research unit, which mission is to promote scientific knowledge and innovation in marine and environmental areas to ensure sustainable, integrated, and smart development. Its organization is around 2 main research domains, which are ocean coastal dynamics and environmental systems and resources. Each of them has its sub-research topics. It's in the second one where the MORE team is inserted. Okay, at the moment we are 4 researchers with different areas of expertise. Claudia Siqueira, she's a professor at the University of Algarve. She's a mechanical engineer specialized in vibrations, maintenance, and condition monitoring systems applied on wind turbines. Theo Moura is a postdoctoral fellow under the project Monitor. He is an oceanographer, and his expertise is in long-period waves and data acquisition. Myself, I'm a Marie Curie fellow under Project Optica. My background is in coastal engineering, and my expertise is in numerical modeling and mathematical optimization. And finally, André Pacheco, he is the former vice director of CIMA, and he is the MORE team coordinator. He is an oceanographer, and his expertise is in coastal process and data acquisition. Related with our projects, right now we are involved in 5 marine renewable energy projects. All of them, they are related with UK institutions. Project SCORE, Sustainability of Using Ria Formosa Currents on Renewable Energy Production, is funded by the Portuguese Foundation of Science and Technology. Its main objectives are to collect data from the operation of a small floating device, to validate models that will allow assessing the environmental impact of energy extraction, and also to develop cost-benefit analysis of tidal energy balancing supply and demand. Our UK partner in this project is Ocean Flow Energy, which is a small medium enterprise based on Newcastle, and their expertise is designing floating structures for the marine renewable energy sector. For those who don't know Ria Formosa is a coastal lagoon based in the region of Algarve in southern Portugal. It's a multi-inlet system where the Faro João inlet has pretty strong currents, and is where we deploy our small device. Project Optica, optimization of tidal energy converter arrays, is my Marie Curie project. The main objective is to formulate and solve mathematical optimization models based on numerical simulations to minimize the levelized cost of energy while decreasing detrimental environmental impacts. The project considers 2 secondments both in UK institutions. The first one was with Ocean Flow Energy, where I get skills using the OrcaFlex software. And the secondment was with the Marine Energy Research Group of Swansea University, where I got skills using a blade element momentum CFD model based in OpenFOAM. Here there is a couple of results applying the bent CFD model with some horizontal axis tidal turbines. Project Monitor, multi-model investigation of tidal energy converter reliability, is funded by the Interreg Atlantic area. Its main objective is to investigate the reliability of tidal energy converters and develop tools to increase it. The project consortium is made of several institutions from Europe, where there are 3 institutions from UK, the Swansea University, which is the project leader, EMEC, and Catapult Offshore Renewable Energy. The other institutions are the University College of Cork, the region of Normandy, University of Le Havre, and there is also 2 tidal energy developers, one from France, which is Sabela, and the other is from Spain, which is Magallanes Renovables. Our role in this project is to plan and coordinate fieldwork activities by giving logistical support to the tidal developers, to collect and process the resulting data that will be inputs to numerical models, and to publish the findings in suitable format. Here you can see 2 pictures of the devices that we are going to monitor. On your left you can see the Sabela D10, which is a bottom fixed tidal turbine, and on your right is the ATIR floating platform from Magallanes Renovables. FLOSPA, Floating Offshore Wind Support Platform Assembly, is funded by the H2020 SMI instruments. Its objective is to demonstrate the feasibility of a floating offshore wind foundation structure, the Star Float. The project leader is Ocean Flow Energy, and well, we are helping Ocean Flow Energy with the proposal writing, numerical modeling, prototype construction, and the setup of preliminary stability test. Here you can see some pictures of the small prototype that was tested at the Royal Coast Marina in Newcastle. Then finally, PAMS, perform an analysis of a multi-float sport for supporting wind turbines. It's a continuation of the FLOSPA project. It's also led by Ocean Flow Energy. Its objectives is to test the device in a wave tank with different wave conditions and wind conditions. We will help Ocean Flow with the data processing. Here you can see two pictures of the prototype being tested at the Cantabria Coastal and Ocean Basin tank. So how can more team help you? Well, we can give support during prototype testing with data collection of mechanical parameters like vibrations, things like that, and also with oceanographic data with flow velocities, turbulence characterization, wave heights. We also can provide numerical modeling, for resource characterization using near source circulation models or CFD modeling. We can also provide a testing area at the Faro Yao Inlet, which is a good place, an ideal place to small prototypes of tidal energy devices and floating wind turbines. This is an aerial picture of the site. This is the Faro Yao Inlet. And depending the region of the testing area, we can find tidal currents up to 2.5 meters per second, or in average 1 meter per second. And well, wave heights are small, around 0.3 most of the time, 0.3 meters, and depending the wind conditions can reach up to 1.4 meters. This is just some of our publications that if you are interested, you are welcome to check. That's it. Thank you.
I welcome José Varandas. Thank you, Eduardo. To stage, CEO for Kymaner, the biradial turbine test at sea.
Okay, good morning, everyone. I want to thank you, WavEC, for having invited Kymaner to talk about this particular innovation. We get asked a lot in Kymaner if we can deliver a turbine in 4 months or 6 months. What I believe most people that do pose that question are not aware of is that every air turbine that is presently being built is an innovation. So it has the natural and typical sequence of events leading to a proof of concept. So 4 months or 6 months is way too short. So what I will be talking about is a process or the result of a process of the development of a new turbine concept. It was developed jointly between the Technical University of Lisbon, the Wave Energy Group, and Kymaner. Kymaner is a Portuguese company exclusively devoted to the development of wave energy technologies, and in particular air turbines. And the example is the Opera Horizon 2020 project. So this project is or what Kymaner delivered for this project was a biradial turbine, which is a patented concept that has a key feature of an integrated valve, high-speed stop valve, which is it's a key feature because it allows not only to protect the turbine from rough weather, rough seas, but also control the flow that flows through the turbine. Typically, when there is a storm, all the typical or the usual wave energy converters shut down to protect themselves. What this valve allows is to what we have been calling peak shaving of this overpower and enable the device to produce even in very, very energetic seas. The type of intervention on the Opera Horizon 2020 project was a demonstration, and it had a series of steps which were essentially the design and the delivery of the PTO, not only the turbine, but turbine generator, the control. What we see in those pictures is the turbine, which is, let me see where the pointer aims at. Yeah, it's not very visible, but it's this green round part mounted on top of a spar buoy owned by OceanTech in Spain. This is the process of final fitting of the turbine. It took place in October, November, early October. It was deployed still in October at sea, and it's being commissioned since then. I mean, waiting for weather windows to actually fire it out. Because we're in a section on innovation, it is important to highlight what were the innovations of the Opera Horizon 2020 project. So the expectation on was focused on 4 innovations to be capable of delivering a turbine that could deliver up to 50% more power than the usual reference, which is a Wells turbine. A different type of tethers that were also manufactured in Portugal, developed in the UK, advanced control strategies, and a shared mooring solution. Another particularity of this project is the open access to 2 years of experimental data at sea. Usually the tests are not very well, or the test results are not very well broadcasted for IP protection reasons. But one of the, let's say, novelties of this project was to make available what those findings were. So you will see, if you fetch the results that have been already published, you will hear about what went wrong and what went well, not only what was particularly successful. The Opera biradial turbine in numbers, 3,000 parts, 4 tons, 500 electrical connections. You can imagine that this has a lot of ground to fail. But, I mean, we have been quite successful so far. Let's see if it goes well through to the end. And the approach to de-risk this particular innovation has been very fruitful, because what was chosen as a path to de-risk the turbine was a very intensive period of dry testing of the already manufactured, ready-to-deploy turbine in the IST laboratory, followed by a test onshore on the Mutriku wave power plant, and that ran across 2017 and 2018. These will be the test results that I will be telling you about. and the final offshore test starting now, any day now, through to July 2019. What you see there is already the device deployed, moored with the turbine on top. Some interesting results related with this expectation of being able to produce 50% more power than the reference. The Motrico Wave Power Plant, for those that don't know, have 16 Wells turbines. And not all of them operate. There are some chambers on the extreme sides that are not currently operating. And there is one position right in the middle that is used to test new devices from manufacturers that want to be able to test in a real environment. And this was the opportunity provided by EVE, the Basque electricity utility, to allow this project to compare the performance with the existing Wells turbines. What we see there is exactly what an experimental result and data extracted from the tests during 2017 and 18, which compares, so in the lower end, the axis is the chamber pressure against the average efficiency. This is a typical Wells turbine response. And this is the biradial turbine response. So one of the things that is striking there is that the average efficiency is actually where the Wells performs better. The biradial efficiency is 50% higher or 55% higher. In the rest of the range, it's way beyond that. The range where it operates is also significantly higher. If you raise the pressure to the right-hand side, we didn't have those pressures beyond the point that is shown there. The higher pressures did not materialize in the Motrico Wave Power Plant, but it's not difficult to assume that the behavior of those curves would be identical. These are a bit more technical charts, but I draw your attention to the lower end. The lower end on the left-hand side, you see the performance of the Wells turbine between negative pressures and positive pressures with the rotational speed, so the speed of the turbine on the vertical axis. The operating range of the Wells turbine and the power generated by that specific device is shown on those painted areas. If you look to the right-hand side, you see that across all of the range, the biradial turbine is capable of producing, and well, the net effect is that the annual energy that can be extracted from that type of turbine is way above what we can expect from the wells. So in terms of the innovation, let's say certification, or the expectation of what was promised on this project, to have an energy production that would be 50% higher of the reference device, it was achieved with success. Now, moving on to a completely different thing. I was telling you that all of our work is about innovation and innovation management and creating new products to be tested. We are happy to announce that last week, a company based in the UK awarded Kymaner with the development and the supply of a new turbine, completely different, which is a 1.5 megawatt turbine. This is probably the largest air turbine that will ever be built, to date at least. And of course, we are proud to announce this here this is the first ever time that we speak about it publicly. So what we will do is to manufacture the turbine and all the ducting that comes with it. So the turbine is this, the centerpiece that's shown in gray, and all the ducting, of course, it involves the design of the ducting, the optimization of those shapes to be able to install in a device, which is a very interesting device, developed by Bombora Wave Power. And it's, I don't show it here because this was not the purpose, of course, but you can look it up in the Bombora Wave Power website. It's a device that has some sort of air pumps, air cushions that push the air through those ducts and make it unidirectional. So there is differently from the Wells turbine, the biradial, where there is a reversible airflow involved in typically an oscillating water column wave energy converter. This is unidirectional, so it more resembles a gas turbine in its functioning approach. So this, of course, like the previous one, will be developed jointly between Kymaner and the Wave Energy Group of IST, the technical university, and we hope to have some more news to tell you 1 year from now, because it will take exactly 13 months to develop. Okay, thank you.